Okay, so what you have seen in this video at the very end, this was basically a TV. Back then, when we just left our caves, when there were 3 programs, if at all, on the TV. And they stopped. You won't believe it, but at night they stopped. There was first a so-called testing picture, and then this was also gone. And that's what the antennas picked up. Or if you very old TVs, well, they had an antenna outside the house, but the antenna was standing on the TV. This was about when I was a very little boy. And I remember a disaster during a European Championship final, which Germany played. My dad was watching it with some mates, and of course, if God didn't wanted us to watch football, he wouldn't have given us beer. Or if he didn't wanted us to drink beer, he wouldn't have given us football. So one of the guys was drunk and then he stumbled against the TV. The antenna was twisted, picture was gone, and then it took always ages to make them. You got it, but in the moment you didn't touch it anymore. Of course, the picture became shit. It was always a fight. But you can imagine this took then 1 or 2, 3 minutes, and this was of course when the goal was scored. Yeah. So old days, ask your grandparents. So basically, this tells us that there are these microwave photons. In fact, there are about 300 or 400 in every cubic centimeter. Universe is big. So this is the leftover from the Big Bang. So let me share screen and then we continue. So basically, these guys that you have just seen, Penzias and Wilson, that you see now here again, they stumbled over the proof of the Big Bang. The most, we had this Hubble expansion stuff. We had the supernova type 1 and confirming it's expanding. So going the way back, it must crunch. But I think one of the strongest proof that there was something like a Big Bang where everything started is this cosmic microwave background. Well, for these two guys got the Nobel Prize for what they suspected to be the dirt of pigeons. So what are we dealing with? We are dealing basically with the light. Again, what we have seen last week, this short story of our universe. We observe now from here, go back in time, go further and further away, and it's the light of the first stars, the formation of galaxies, and then the structures that we have nowadays. And this strange re-acceleration. I will later talk again more about this. Okay, the Dark Ages, and then the Dark Ages started basically when light could freely propagate through the universe. And this light back then, we observe now as microwave background. And what you see here, WMAP, is the Wilkinson microwave anisotropy probe. Before we can't see. There we really need lab or bigger labs like CERN. So, but this expansion of the universe, well, there was this Lemaitre, but then there was another guy who used basically Einstein's general relativity. A guy called Friedmann, that means basically peace man. He came up with this equation describing the expansion of the universe. So what is this equation? Well, what enters here is this Robertson scaling factor, which gives us basically the size of the universe at a given time. That's a rescaling factor. Or Robertson-Walker scale factor, whatever this exactly is. Well, on the left side we have the Hubble constant, the square of it, even. Or Hubble parameter, Hubble constant, whatever you want. I think it's rather parameter because it might change with time. Which is defined as this velocity over distance. If you remember last week, there we had basically plotted the velocity from the redshift over the distance of an object. And then put in the straight line, and the Hubble constant was the gradient of this line. So basically velocity over distance. That was last week. Velocity over distance, so we can know the scale factor at a given time minus the scale factor at the second time, which was probably before the time of the first one, divided by the time difference. So length difference, some way, divided by a time difference. If you let the time difference go towards 0, this becomes directly the gradient. That's the definition of a gradient. We get a velocity. And this is renormalized by the scaling factor. This is the Hubble constant, which gives us basically the expansion rate of the universe at a given size, or velocity over the size. Okay, so this enters basically the dynamical properties suddenly of a universe where Einstein didn't believe really in. He wanted a steady state universe. So once created by God, it stays all the time the same. Thanks to Hubble, we know there is something dynamic going on. Or again, Edwin Hubble. Leading now to this history of the universe. What else enters here? Well, the second part is minus kappa over c squared, where c is the speed of light divided by a squared. Again, some inverse time here involved. Velocity, way over time divided by way. This must be 1 over time, then squared of, obviously. They're in the same dimension at least. And this involves basically the curvature of space. And what we had here now, locally by one mass, it might happen on a very, very global scale in the entire universe that the geometry is bent on a very big scale, not only on the small scale around the mass. This is really the entire universe. So we can have a flat universe where the sum of angles in a triangle would be 180 degrees. Given on a certain parameter, we might have a closed universe, so deformed that somehow everything is meeting again. Or on this certain parameter, which is now called omega, we can have an open universe. And the sum of angles would be less than 180 degrees, and here it's a bit more than 180 degrees. Is this right, what we have learned in school? Locally, it seems to be relatively well fulfilled, more or less. We don't even feel this curvature that is in space on Earth introduced because the Earth is there, a big mass is nearby. So we have here this property of space again, the expansion rate of space, of the universe, this overall curvature of space. Then here, this vector, we had gravitational constant. If you remember this Einstein field equation, there was on the right hand side basically this factor a pi over g over 3, where g is again Newton's gravitational constant according to Newton. And then we had there this energy stress tensor. And this energy stress tensor is now here replaced by what is called an energy density or energy per volume. This energy per volume, well, energy density of in the entire universe. So much energy do we have essentially. So depending on this energy density, because the only stuff that is really working on this long scale against the expansion of the universe is gravity. So we have a force that is pointing inward. We have a surface that is given. We would get for an inward working pressure force per area. This is a pressure, inward working pressure that slows down the expansion rate. That is referred to only gravity. So, and this omega that we have seen that defines basically here now the geometry of space is given as a ratio of what is there in energy density in the universe divided by a critical value. And how can we define this critical value? So omega, well, we have now, there is enough stuff, or there is not enough stuff. So the gravity is too small and the stuff always keeps expanding because it works, this inward pressure is not sufficient to completely stop the expansion. This would be, if we have the expansion over time, be this part of the upper part, an open universe, which is ever expanding. Well, then we can have a critical energy density that's too much. So the gravity is so strong, at some point the universe comes to a standstill, and then the gravity is strong enough to start contracting it. This is called a big crunch. From the Big Bang to the Big Crunch. What happens afterwards, we have no idea. It's just pure speculation. We talk of a closed universe, and then of course the critical, it's just enough that it comes to a standstill. There's no more expansion. We are back. We are really at the steady state universe, which would be the open universe and the steady state universe. I don't like them because this means the very end of time, it's just dark and cold. Not really appealing, well, rather everything collapsing and crashing again and ending than just dark and cold until eternity. Okay, so hopefully you got a feeling how important this critical parameter is, and now what enters this energy density. Well, the classic is, of course, you have radiation, electromagnetic waves. They can obviously move some or bring signals and make currents in the receiver antenna move, so able to work. There must be some energy. So radiation density is there. Then, of course, matter density. And matter, of course, if it forms space in deformation, is always some energy stored. The more you deform, the more energy, and if you deform too much, then you have a crack. That's called Hooke's law. It's probably not for, hopefully not for space. So we have then also this spatial curvature density, which obviously also can store. Oh, So far, so good. But now we have seen, well, if you remember this cosmological constant that Einstein introduced in his equation, in case it does not have just a steady state universe, in case the universe starts to expand, accelerated, like we have observed with this supernova stuff. At the last couple of billion years, it starts to expand accelerated. The opposite what should do. So basically there must be stuff that works towards outside with a negative pressure. And out against gravity. So suddenly there must be something in the universe where we have no clue what it is. Some type of energy. So suddenly we need this term again from Einstein's cosmological constant. So it's necessary, and you remember what Einstein said, it's the biggest blunder of his life. And we would know, because we have no idea about this energy that is basically causing this reacceleration, we call it dark energy. More. So no idea what it is. And how much there is, we're going to see at the very end. So basically we have this expanding universe, which was at the very beginning very fast expanding, but then deaccelerates thanks to gravity. And seemingly there was no, or if dark energy was there, it wasn't too much. And at the beginning we had this very hot temperature, so every time an atom formed, there was a photon coming along and separating. And now we're going to look more deeper what happened here at this time. When basically the universe was so big that the energy density dropped, the temperature dropped. What happens there? This will be in the next video. We talk then basically really about the microwave background, where it's coming from, how it's observed. And then in the very last video we talk about what happens, or what can we learn from this. I'll see you then. I try now to avoid to make the videos too long.